Hey programmers, welcome back to day 10 of the Advent of Code. So let's take a look at what today's input looks like. It's really just going to be a bunch of different numbers, positive numbers at that. In the context of the problem, these numbers represent different voltages and we have to find some compatible power adapters basically. I'm going to kind of forego all of these story elements in this problem and just focus in on the algorithm at hand. So basically, now that I have all of these numbers, what is my actual goal? Well, what I want to do is find an ordering of these numbers. I want to basically start at 0, and I have to get to a point that's 3 larger than the biggest number in my list. So if I look at my biggest number, that would be the 19 over here. If I add 3 to it, that would give me 22. So basically, I want to sequence these numbers in a way where I go from 0 through 22. And with that, there's also a constraint in the problem where from one number to the next, we can't make a leap more than 3. So kind of formally putting this problem, what I have to do is arrange the numbers in such a way that they form a sequence where the numbers increase from 0 to 22 with a max difference of 3. So how can I start attacking this one? Well, I think it's pretty straightforward. If they're saying that there is such an ordering that goes from 0 to 22 with the max difference of 3, one way I can get that ordering is to just sort these numbers. And that would be fairly efficient running in just n log n time. And so if I just sort these up, I end up with something like this. And really in the context of this problem, they ask you for some very particular results. In particular, they want you to count the number of adjacent differences that are 1, as well as the number of adjacent differences that are 3. In other words, if I look at this gap going from 4 to 5, that would be a difference of 1. And another example would be going from 7 to 10 would be a difference of 3. If I counted up all of these, I would find that there are 7 differences of 1 and just 5 differences of 3. And in terms of the return value for our overall solution, we just want to take these two numbers, multiply them up, and so our final answer would be 35 in this very short example. And so that sounds very reasonable to implement, really just some sorting. Let's hop to it. All right, let's go ahead and implement part 1 together. So here I have my large input file. Hopping over into my solution file, we'll just start as always by reading the lines from the file. I'm going to split on the new line character, so that'll give me an array of strings. What I definitely want to do is convert each of these strings into an actual number, right? So what I can do is const numbers equals lines.map and just turn each of these into a number by using the number constructor, right? Cool, so that'll give me the numbers. Let's just see what that looks like. Console.log the entire numbers array. So we'll give it a run. Nice, and there I have a nice array of numbers. But what I definitely want to do now is sort these up. So I'll just use the built-in JavaScript sort. So what I can say is numbers.sort. And I pass in a callback that does the sorting in general, taking any two elements of the array, A and B. And I can just say, I believe, A minus B. I don't remember if that sort's increasing or decreasing. We're about to find out. That should give me back a new array, right? So important thing to know about the dot sort method, it is not in place. So I'll save that as const sorted. Then I'll print out the sorted array. See what that looks like. Cool, yeah, so if I do A minus B, that gives me increasing order, which I think is what I want. All right, now that I have this sorted array, I actually want to add some elements into it. So according to like the prompt, sort of implicit elements of this logical array would be 0 at the very beginning, as well as looks like 150 at the very end, right? So I always have 0 at the front, and then my last element should be basically the largest element of the original list, but plus 3. So I'll go ahead and add that into the mix, and I want to have them actually exist inside of my like input array, we'll call it, just so that I don't have any weird off by 1 errors, because that's super annoying. I'd rather just collapse that into the generic code, right? So let's say I do const the last element. So the last element would just be the last element of the sorted array. So sorted at index sorted.length minus 1. Since it's already sorted, I already know what the maximal is, right? And then from there, I can create my true input by putting 0 at the very beginning, followed by everything from the sorted array, followed by the last element plus 3. So we'll see how that looks like. That'll give me my main input, which will be great for both part 1 and part 2. Nice, starting with 0 all the way to 150. Cool, so implementing the core algorithm for part 1 is straightforward. Just need a count of all of the steps of 1 and steps of 3. So since the generic algorithm for just counting the number of steps of like n is pretty straightforward, let's create a helper function to do that. So I'll call this maybe diff count. It's going to take in some array and also some value, I don't know, n. And I want to return the number of times that elements in this sorted array have a difference of exactly n. So I'm definitely going to assume that the array argument on line 18 is going to be sorted, right? So what I'll say is, create my count, which I should definitely say let start at 0, and then just count the things, right? So figuring out the difference between two adjacent elements is just about, looking at your current index position as well as the one right after it probably, right? So let me say for let I equals 0, go through the entirety of the array, but I should probably stop one iteration early, right? The reason is I'm going to look ahead by 1 unit, right? So imagine that I is the last index of the array. If that was truly the case, and I'd look out of bounds, which I kind of don't want to be safe. So what I'll say is, because my current element is array at index I, then my next element is array at index I plus 1, and I better call that next. And since I am assuming that my array is in sorted order, if I took the difference of the next and the current, that should be exactly the n, right? So if it's the n, then I better count that thing, right? So I'll do count plus equals 1. Maybe plus plus is better here. Cool. And then afterwards, after I'm done iterating through the entire array, you can go ahead and just return your final count. Cool. And with this one helper function, it keeps my main solve code pretty clean. I think it's just as simple as taking the diff count of the input array, rather. Notice that the input array has the 0 and the final element in it. So I'm using that array. I'm trying to find diff count of 1 and diff count of 3. But really, I guess they want us to multiply them. I never understand why they want us to do that in the actual, advent of code. I'm guessing it's just how they check the results. I'm not sure why though. It's kind of arbitrary, but if we should, then we will. So let's see what this results in. I should get 1,848. I have this pre-calculated result, right? And this does pass at least my test case. Hopefully you're trying this on your own input file though, right? So let's run part 1. Nice, and there we have a straightforward solution to part 1. Let's hop back into the drawing board and talk about part 2 now, right? All right, now let's talk about part 2. Part 2 asks a much harder problem. Here I have listed the same numbers as before, and they're still in sorted order, but this time we can formalize a different question for part 2. Now we want to figure out in how many ways can we move from the 0 to the 22 if we may only move to a number that is at most 3 greater than our current number. So what does that really mean? Well, basically we have a set of rules for traversing through this list of numbers. So let's say I start at 0. You really only have one option here. You can only move to the 1 right next to it. That's because the difference between 0 and 1 is 1, which is definitely less than or equal to 3. You couldn't step to the 4 because that difference would be too great, and of course you wouldn't step to the 5. Right? We know that since these numbers are in sorted order, once I find some number that's out of my range, nothing else is going to be in my range, right? Let's say I were somewhere else, kind of just randomly. Let's say I was currently situated at this 10. Well, I have a few options here. I could move to the 11, because that has a difference of 1, or I could move to the 12, because that has a difference of 2. But I cannot move to the 15, because that has a difference of 5, which is greater than 3, right? So those are our rules for traveling through this list. Because from any given position we have multiple options of where to go next, then it's pretty evident that there are going to be many different ways to travel from 0 to 22, right? In some ways I may touch certain positions, and in other ways I may not use up those positions. So here's what we should do. Let's come up with a general algorithm that we can use to count the number of ways to get from 0 to some target number in our list. I'm not going to step through the full 0 through 22 because that would be way too large, for a reason we'll speak about in a little bit. So let's say that I trim my input, and let's say that my goal is to get from 0 to the 10. So we'll kind of ignore the rest of the input. But I know that if we could come up with a well-formed algorithm from going from 0 to 10, then we can scale this into any arbitrary target. So let's start reasoning this one out. Whenever I'm given a problem where I know I have to make a decision process, I start by visualizing that as a tree, really a decision tree. So what I'll do is kind of envision all of these different numbers, which were elements of my list, as basically nodes or like states of where I'm currently situated on the board. So we'll kind of move these down below. And how do I start my decision process? Well, you don't really have any options here. You definitely must start at the 0. So that'll be the root of my decision tree. And then from there, I can only transition to very particular nodes. In this case, the only node that I can move to next would just be the node of 1. So I'll add that as a child from the root. At this point, let's say I'm situated at the 1. Well, again, I have some limited options for where I can go next. If you look at my items at the very bottom, the only thing in range is the 4. So that also appears as a child. Let's say now I'm at the 4. Well, here's where things get interesting, right? From the 4, I have an option to go to the 5, 6, or 7, because those are all within my maximum range of a difference 3, right? So that would give this node of 4 3 children, right? I have some options here, and so I have to branch out a little bit. Let's say that right now I'm currently situated at the 5, right? Well, then from here, I just have more options again. I can take the 6 or the 7. Let's say I'm at the 6 on this left-hand side. Well, I only have one option, just a 7. And then from that 7, I must go to the 10. And that's just one path we can take from the 0 all the way to the 10. But we have many paths, right? So let's flesh out the rest of this tree. So if I look at this 7 node over here, it'll look like this. Look at the 6 node over here, it looks like this. And if I look at this right-hand 7, it looks like this, right? Using the same reasoning we did for the rest of the tree. And so looking at this tree, I'm going to argue that you have your answer for this problem, right? How many ways can you get from 0 to 10? Take a moment, stare at this, and figure out where you see the answer. So what's the answer here? Well, there are 4 ways to travel from 0 to 10. You're probably recognizing that if I look at the leaves of this tree, the ones that terminate in 10, basically all of the leaves, those represent each of the ways that I can travel from 0 to 10. But how can I actually do that programmatically, right? I think, when it comes to these algorithms, the hard part is actually writing a picture like this in the first place, right? Where we follow some well-structured algorithm and we don't do any weird, heavy-handed conditional logic, right? I followed the same rules at every node of this tree. But then how can I actually implement that in my code, right? It's kind of different from just drawing a picture. Well, whenever you have a tree, you should be thinking, at least in my opinion, recursively, right? So imagine that each of these leaf nodes that have a 10 inside of them, those represent me kind of already being at my target. So if I'm already at my target, in how many ways can you get to the target? Well, that's really just a base case, right? There's definitely just one way to go to your target. Just stay there and do nothing, right? You're already at your winning position. But then from here, how can I build up on my larger solutions? Well, let's stay focused on this left-hand side right now. I know that when I return values, those values return back up to the caller or the parent node in this drawing. So I'm going to bubble up this one a little bit. I'm going to bubble up both of these ones. And here's what happens at this 5 node, right? This 5 node is going to receive back a 1 on its left path and a 1 from its right path. And what this node should do is just add up that 1 plus 1, giving me 2. And if I do a quick sanity check at every point of this return, what I should be doing is having logical answers, right? And so above the node of 5, I have the return value of 2. And that makes sense in itself because if I start at 5 and go to 10, there are 2 ways to do that. And then from here, I can follow that same general logic to complete the rest of this sketch, right? So I can bubble up these guys a little bit. Now at this 4 node, it's going to have the job of adding up the 2 plus 1 plus 1, which results in a 4. And then this just bubbles up all the way to the top, and there I have my final answer of 4. So that doesn't seem actually too fancy, right? Just some classic recursive code. But what we should be aware of is the size of our input. Think about the worst case scenario. You know that from any given node, it's going to have at most 3 children, so it has a maximal branching factor of 3. In general, if I had n nodes, then the size of this tree would be 3 to the n, which is exponential. And so that's going to definitely be way too slow for anything over like 30 nodes, right? So overall, we want to kind of figure out a way to efficiently implement this algorithm. And we can actually realize this still from the tree diagram. That's why I think drawing an algorithm is almost more important than coding it. If you stare at this tree for a little bit, can you recognize any patterns? Well, something I recognize is there are some duplicate subtrees. If If I look at this node that starts at 6, it actually forms the root of its own subtree, the 6, 7, 10 subtree. I can find that subtree here, but I also see it over here. That is, this subtree is duplicate. I know that when this node of 6 returns its result, it's going to be the same result that it would return later on as well. What you might also even notice is there are plenty of duplicate subtrees. Right now we have highlighted the ones rooted in 6, but there are some subtrees that are duplicate rooted in 7. And I know that what I can do in the long run is implement memoization, or really just a cache that maps my arguments to my recursive function to their return values, right? When I make the same recursive call down the line, I should just be able to look up its return value in constant time if I calculated it previously. So overall, this is really looking like a very traditional dynamic programming problem. With all this being said, let's hop to it. All right, let's code up part 2 now. So I'm going to start by just laying down most of the code we had for part 1, but we don't need this difference counting stuff. So I can take that out here as well. What we really want to do is implement that recursion tree, right? So let me build a function. And if I called it, let's call it, I don't know, numways. And I'm going to pass it this input array. Cool. And so how do I think about this one? I'm going to define this numways function. And if I really stick hard and fast to the drawing I drew of how the tree explores its nodes, then that should have a one-to-one correspondence to the code I write right now, right? So we're going to stay very, very contingent on the tree. And so we'll take in the array, let's say. And let's think about how we're going to actually run this algorithm. So whenever I'm implementing some recursion tree, or in general, recursion, I think about my different calls, right? So passing along the entire array is pretty good, but I also need to know my current position. And the way I'll denote that is by maybe starting always at index 0. So I'll just use some JavaScript default arguments. You could if you want to, or you can just pass it in explicitly. So I'm definitely going to start at index 0 of the array. Cool. And so if I'm going to think about this recursively, then why don't we just start with the base case, right? So in the context of the tree drawing, right, we were able to hit our base case and terminate our recursion whenever we hit the last element of the array, right? In the context of our earlier drawing, that was like the node whose element was 10, but in general, it's just going to be the last element of the array. And I'll just check that by using this index, right? In other words, if my index is the very last position of the array, so array.length -1, then you must have just found a successful way. And that represents 1, right? So return 1. Cool. Very consistent with how we started to combine those return values inside of our drawing from earlier. But now here's the hard part. How can I actually get like the branching effect here? Well, if you draw a tree to trace your algorithm, then the branching comes from making recursive calls, right? So let's start to tackle this. So I know I'm going to call numways. And we said that something inherent in this problem is from any given node, we could branch at most 3 times, right? Depending on whether or not 3 elements are in range, right? So I know in the kind of worst case scenario, when I have the most number of options, I would have to actually use my next 3 neighbors. Something also kind of inherent in this problem is I don't think they give us any duplicate numbers, right? So we'd be okay to just look at exactly our next 3 neighbors, we'll say. Only to the right, though. We're never looking backwards, right? So let's say, I don't know, I looked at the array at index I+1, and I+2, and I+3. This is kind of a habit I have whenever I kind of don't know how to start writing the full recursion. I just know there are certain like patterns that I need to combine. So I'm going to make some recursive calls. I definitely want to look at my next 3 neighbors and do stuff like that, right? So I think we should finish mocking out what at least one call should look like, one recursive call that is. Well, I know that the array never changes. What should change is the position I'm at. So what should change is the I. And something consistent with that is, well, I expect I to be a very large number in the long run, right? If it hits the last element of the array. And this is exactly increasing I by some value. So now I'm going to have the overall effect of jumping to each of those future positions sometimes, right? But not all the time. And so I need to actually check and make sure that, hey, those places that I leap to are legal right now. In other words, they should have a difference from my current position that is less than 3. So now I'm starting to really see the big picture of things. So here's what I'll do. Let me start to write a conditional. I'll just write it for one of these expressions, and it'll probably be symmetric for the other two, right? So here's what I'll check. Hey, if the difference from my next element and my current element, so I'll say array at index I, right? Remember that I'm currently at position I, and my next position right now is I plus 1. So if their difference is less than or equal to 3, so if that thing is less than or equal to 3, then I'm actually okay to jump there. So then I'll nest my code like this, right? Nice. And so what we also have to be aware of is whenever I have this pattern of looking ahead in an array, I also want to make sure that I'm in bounds. So maybe a quick way to do that is just use a little and clause here. So I'll say, hey, if array at index I is truthy, then I can actually look forward in the array. Cool, that's looking pretty good. And I think what I'll also do is probably add another parenthesis here. Am I missing one here? I'm missing one here as well. And I definitely need to say I plus 1 over here, right? So what I'm checking is, hey, if my next position is in bounds and that next position has a difference relative to my current position that is less than or equal to 3, then I make that recursive call. And I do basically the same logic for I plus 2 and I plus 3. So here I have all 3 of my recursive calls wrapped in their respective conditionals. And I love how symmetric this code is. I'm feeling like it's really consistent with what we drew out. However, I need to start working on my return value, right? So important thing with recursion is I'm always sure to match my types. So I'm definitely in my base case returning a number. And that means at any point in time, I assume that these calls all return number data. And in particular, what they'll do is give me back the number of ways to get from position I plus 1 to the very end, or the number of ways to get from position I plus 2 to the very end, right? And I want to figure out the total number of ways, right? So I just want a running sum basically. So I can say let my total equal 0. And I'm going to basically add into that total all of the ways if I decide to do a plus 1 move, and all of the ways if I decide to do a plus 2 move, and all the ways for a plus 3 move, right? Giving me that branching factor of 3. Something that makes me feel good about this code is when I drew it out earlier, I had a parent node add up all of the number results from its children, right? And that's exactly what this code is doing, right? The parent in my kind of logical code right now is my call, and then the children are these recursive calls, and I'm definitely just adding all of them up, right? And then from there, as a parent, I can just return that total, and that should be good to go. So this is really just the brute force solution. Notice how short and elegant the code is. I love symmetric, recursive code like this. Let's run it. It's probably not going to halt in any reasonable amount of time because this is going to be 3 to the n, right? It's going to be exponential, which just explodes in terms of the size of the tree. But don't worry, we know exactly how to fix that. Just a classic dynamic programming problem, right? So I know that I'm going to have duplicate subtrees to explore, and there's no point of exploring a tree twice over, right? The result for that whole tree isn't going to change, right? It's invariant. So what we'll say is, the way I like to implement dynamic programming with recursive functions is I bake in a nice memo object up top. It's going to map the arguments to my function to their return values, right? I don't need to include the array as the key in my memo because the array does not change, right? I need all of the information that uniquely identifies the return value. If every node of my tree has the same array argument, then the array doesn't really identify its return value, right? But the I is definitely going to be unique for my nodes. So what I'll say is, if the value of I is inside the memo, so if that's a key, then you must have been in that node before, so just return its stored value. So I'm assuming that the first time I explored it, I did the nice thing and saved that information for a rainy day, right? So memo at I. Cool. So I added that additional base case, and I'll be sure to definitely pass along rather, this memo object. I want this memo object to be kind of like a global, I guess, or shared among all of the recursive calls in the same recursion tree. And this is how I kind of duplicate that, right? And then from here, how do I actually add things into my memo? Well, it's just about taking my literal return value, putting it into my memo object. Something like this, we'll say memo at I. Put that return value in the memo object using the same key, but still complete your return. So I can still return total, right? So that's really all there is, I believe, to memoizing this one. Like I always say, memoization is only a very, very like superficial addition to your code after you solve the brute force, if you used pure recursion, right? Which is why I love to do things recursively. So I should get this large number, starts with 809, if this code is in working state, right? So let's give it a run. Node part 2. So I get back undefined, and there goes the punchline, lost forever because I didn't return this. That's always super annoying. So let's see if this works. Nice, and there we have our solution for part 2. So there we have it. I do think that this is a really interesting problem, but if you can kind of get rid of all the noise, it's really just a classic counting problem that we should implement using dynamic programming, right? Core sort of data structures and algorithms that remind me of this pattern that I use to kind of make a breakthrough on this problem is things like Fibonacci, or more maybe on the nose, Tribonacci, whenever I have this kind of three-way branching logic. So that's all I got for today's video. I'll catch you tomorrow for day 11.